Let's get started. Got a lot to cover today. As a reminder, we have an exam Thursday. Today. We have an exam Thursday. No. Um, shoot, yeah. I'll just do a one question exam now. So today is going to be our exam review. I'd mentioned this when this was like half the people in here, but I did post these slides. If you guys want to review it right now, you can. What I recommend doing is like for this, there's not much like fill in the blank. It's more so just like I'm going to talk about the process and like kind of make some notes and stuff. But the lecture shell itself is not as much of a shell. It's more of like a presentation, you know. So like all the answers are on here already. Review the solutions, and I'm really going to try to break down like the methodology of how to solve it quickly. Hey guys, Lance, sorry, dude. Sorry, I'm just starting and I don't want it to pick up on the mic. Thanks. So review these as I go through them. And then I always recommend too, like some of these problems, it just takes a little while to go through them, like repeat them, you know, write down, even if you've already solved it once, solve it again. And it kind of helps cement the process and the thinking in your brain. There's two primary topics on the exam. And we're going to go over a little bit about what to expect for it. There's the torsion, which we talked about way long ago, right after exam one. So I know that was kind of hazy for some of y'all. So go through those slides again and make sure, and we have some examples here to go through. But how to understand internal torque based off of external applied torque, how to find twist, which is this twist, and then also how to solve external reaction, or sorry, how to solve indeterminate structures using those compatibilities when it comes to twist. So remember on the last exam, we talked about this using thermal and compatibility and superposition of point loads and deformation. We can do the same when it comes to twist, setting the points equal to each other where you know the twist is going to be equal to each other. In terms of beams, this is a little bit more linear in thought, right? We have understanding shear and moment diagrams. So back from statics, know how external loading produces reaction forces, which produces a shear diagram, which produces a moment diagram. And then based off of this shear and moment diagram for this exam, all we care about is where the max moment is. And then based off of that max moment, how do we find the flexural stress, which is a type of normal stress, which is this, a sigma. And then also, how can we estimate deformation from the radius of curvature? So remember, well, we'll talk about it more in the example stuff, but how to find the radius of curvature from that. So really like the beam side of things is kind of linear, I think, you know, shear moment, flexural stress, radius of curvature, kind of like following the steps down. Make sure you go back and review the torsion aspects, because torsion is kind of like similar to exam one, where you have to find internal things. I could be asking about the twist angle. I could be asking about shear stress. I could be asking about torque, that kind of thing. So they're all kind of related. Let's look at what's given to you. So a quick notice on this. This has been updated for the four of you who actually downloaded it and looked at it. I did add an equation that I forgot to before. That's this one right here, shear stress due to torque. So if you've already like started reviewing the exam 2 formula sheet, you'll notice that's not on there. This is how it will be printed and given to you exactly like exam 1 on that first page. You're welcome to peel it apart. I'll bring staplers, you know, whatever you need to have these by your side. What you'll see I'm not giving you for a lot of these things are the definitions of the terms. So like deformation due to torque, obviously that's twist. You would need to know what this L represents and what the G represents, right? Like, because that's not given to you on there, you know, shear modulus and the length. So make sure you're familiar with what some of these terms mean. The C, right? This is centroid, or this is the distance to the centroid, or the center. So just some of these things like that, like what these actually mean physically for it. And we'll also be going through some example problems here too to help solve this. So just making a note of what these represent and what you're going to be given. So format wise for this exam, similar, but less conceptual. I'll just say that, right? Like there's exam one was heavy conceptual when we're talking about definition of terms from a stress strain relationship, like Hooke's law and all that stuff, and Young's modulus and all that. And as I said before, those things will carry over to this exam. Like obviously you see a shear stress here, and you see a normal stress and a strain here. Like, so conceptually they carry on, but not like heavy like cumulative nature. But still similar, where we're going to have a true and false at the beginning. There's going to be multiple choice, and then there's going to be numerical problems at the end. So similar kind of format for it. Any questions in general aside from exact specifications on the exam? Yeah.
Where is this located?
So under files, it should be, if you go to files on Canvas, I don't remember if there's a subfolder or something, but yeah, it should be in there. But I have not updated this, so that's the old one. So I will update this one tonight. So if you go to download this now on Canvas, just know the only thing missing is this one. This will be added on there. Okay, regarding exam one, if you haven't picked up your exam yet, like, because I just brought them into class that one day and it took like 15 minutes to get everything sorted out. So I didn't want to do that again. So just follow me after class and you can pick up your exam if you're interested. If not, and you don't want it, I'll hold on to it until I burn them all at the end of the semester. I'm fine with that too. All right. So what we're going to do is go over homework 3. And then what you'll see in here too is I've added a few additional, what is going on? I added a few additional practice problems. As I said before, the way I'm solving these on the homework is what I think the most efficient way. There's some ways, there's different ways to solve them. So keep in mind though, like maybe as I'm going through the steps, you're like, oh, I didn't do it that way. It always helps to like go and see the different ways to solve them and practice those different ways. So sit back, watch all of the slides and stuff. If you have questions, raise your hand, I'll answer. But I still recommend going through this video after, like tomorrow or something, just doing some of these problems again that you weren't clear on how to solve it. All right, so this one is a torsion problem. This was from problem 1 on our homework. We're told that it's a solid shaft, which is important, right? That means the cross-sectional geometry is going to be a solid circle. And it's subjected to all these gnarly looking distributed torsions and point torsions. Now, if you're like me, when you first see this with a bunch of arrows, you're like, what the heck is going on? Like, how the heck am I supposed to solve this? But what I think is easiest is if you have a torsion problem like this with a 3D looking thing like that, always try to visualize it in a 2D or profile space, which I'll show here in a second. So we're asked to determine what is the required diameter of the shaft if the allowable shear stress of the material is 1.6 megapascals. So in this case, we're given a material constraint saying this is the allowable shear stress or strength. We can't change the material, but what we can change is the outer diameter. Now, what we know is shear stress is distributed like this across the triangle. Sorry, I should have drawn that bigger. Let me just restart that. So if this is the cross section of it, then that's just a normal circle. Shear stress from rotation from a torque gets bigger the further away you go from the center. So I'm not trying to draw Pac-Man or a smiley face with a grill. That's a gradient going away from it. So the outermost fibers experience the most shear stress. So if we're talking about drawing this from statics wise, what we first need to do is solve for this support torque or support reaction here, this torque at C. But instead of trying to draw it all in 3D, let's draw it from a 2D perspective. So this little thing is just a little profile view of it. And what I'm doing is I'm just saying essentially, okay, a clockwise is going to equal an up arrow and counterclockwise is going to equal a down arrow. The way we have that shown there. Hopefully it's kind of clear to see how I'm getting from this thing to the right that is in 3D and kind of confusing looking to this profile view here. So we need to set a support reaction, and we're just going to say it has this clockwise. So sorry, we should just to be consistent. Let's say it has a support reaction that way. Now, when we view it this way, we can set up our statics equation of the summation of torques, but essentially what it looks like is the summation of vertical, or summation of y, or sorry, summation of forces in the y direction, right? But essentially what I'm saying is, okay, it's really the summation of torques at C is equal to 0. And then we're going to say this up direction is the clockwise or the positive direction. And so our static equation looks like this, and really our distributed torque there of 2 kilonewton meters per meter is shown by that resultant force here. So this is that resultant force of the distributed load or distributed torque. So the thing to remember with this is, since these are torques, we don't multiply them by a distance. External moments or external twists on our shaft, it's not like a force times a distance that you would see when you're doing summation of moments. Think about these torques are all applied across this axis here that I just showed. Let's just call this centroid. That's centroid here. So the torques are being applied across that. So it doesn't matter about how far away it is at point C. We're taking the torques across the centroid, that C, at the little kc, not big kc. So if we do this math out, we get a torque at point C of negative 1,400 Newton meters, which just means it's the opposite of the arrow that I drew in the original spot. So it'd go the other direction. So we have the torque across the entire thing. So what we would need to find is, where is the maximum torque within our little solid shaft that we have here. So similarly, how we would do a shear diagram, we're going to draw a torque diagram. And so same notation, where we have, it starts off with a negative 1,400 from our support reaction. And then we have this distributed torque of 2 kilonewton meters per meter. So we know that in total, this is going to be 2,000 Newton meters times 0.8. So that's 1,600. And so we add 1,600 meters, Newton meters to it. And then we have that point torque of 600. So we knock that down 600. Right. So this is minus 600. Then nothing happens in between here. And then we have that end torque going back to 0. So similarly to how we've been doing with the shear and how we're doing with the moment, this is needed to determine where the max is. Because we know that T max is going to produce the maximum shear stress. So that max torque is going to be 1,400 Newton meters in this direction right here, right? So that's our max value. Even though it's negative, remember the negative just tells us direction. So it's still the max total value that's going to be included in it. So this is our maximum. So our allowable shear stress, or really you could just get rid of this allowable here. Our shear stress due to torque on our sheet from beginning is this is this equation. The torque times the distance radius from the centroid divided by J. And what is J? Yeah, polar moment of inertia. Yeah, which is a geometric property, and we're only doing circles, and that equation's on your front page too. So remember that is going to be in length to the 4th or something. So we're setting this equal to 1.6 megapascals because this is our allowable. This is the constraint of that. So that's why we're setting this to the allowable here. Remember, polar moment of inertia, I show it in terms of diameter here. I think on the first page, I have it in terms of radius, but it's either pi r to the fourth over divided by 4 or pi d diameter to the fourth divided by 32. Okay, problem 2. We have a steel shaft with a diameter of 40 millimeters. It's fixed at both ends, A and B, and is subjected to this couple force shown there, the 3 kilonewtons, causing this counterclockwise rotation, or whatever way you look at it. We're asked to determine the maximum shear stress in regions AB and CB of the shaft. And we have a material shear modulus, G, of 75 gigapascals. So maximum shear stress. Maximum shear stress is this. And what we just found before was we know it's going to be torque times the radius divided by J, the polar moment of inertia. So we need the internal torque before we can find the polar moment of or before we can find the shear stress. We know the radius, right? Because we're told diameter. And we can calculate J because we were, again, told the diameter. But what we can't find is the internal torque. And we can't do that because using statics right now, it's an indeterminate structure, right? We have this external torque applied shown by that, that blue arrow in the middle. And then we have the two fixed ends A and B that are producing a fixed torque or resistance against rotation. And if we just do the summation of forces in that area, we can't solve for that. So let's first find, since these are given in forces, let's first find the resultant torque applied here by looking at this like little profile here. So what we're essentially given is, okay, we're told that it's a 3 kilonewton force acting 50 millimeters away from the center. So remember, the torques are all applied across this centroid axis here, this centroid axis here, this center. So we use that distance away of 50 millimeters. Now, this is essentially saying, since there's one in each direction, this is essentially saying there is 6 kilonewtons in one direction acting 50 millimeters away. So the total torque applied across that center line is going to be TA, which is unknown, TB, which is unknown. And then I just put it on the other side of the zero, right? Because it's in the opposite direction. But we're going to say that this is 6,000 newtons, which is 6,000 or 6 kilonewtons, times the distance 50 millimeters, which is 0.05 meters. So just make a note that I already did that math and transferred the units over already.
Excuse me. Why do you multiply it by the 0.05?
So yeah, this is what we're looking for, is the resultant torque or twist here at this torque at C. So we have a force that's given of 6 kilonewtons, and that force is acting 50 millimeters away.
So you're doing it because it's the outermost part of the square, whatever it is.
Well, that's just where it's applied, like based right here, 50 millimeters. So a torque is a force times a distance. It's essentially a moment.
Okay.
So in this case, we're just given forces of 3 kilonewtons.
Okay.
So that's the resultant torque. Now this, I put a ... one, which means obviously we're going to need a systems of equations because this is two unknowns and we can't solve for those two unknowns like that. But this is still an important equation. What we have to use now is compatibility of the twist angle. So what we do know is at this center point here at C, the twist between C and A in this first section is going to equal the twist between C and B. And why do we know they're going to equal to each other? Yeah, they're connected, right? Yeah. So it's like if you grab a pool noodle and twist it in the center, like the twist on this side of the pool noodle is going to equal the twist on the other side because they're connected at that point in the center. So that's what essentially is happening here. The twist between C and A is going to be equal to the twist between C and B. And we have an equation for twist. And luckily, in that equation for twist angle is torque. Now, the other things in this is length. So the length of that specific section, the J, which is the polar moment of inertia, and then the G, which is the shear modulus of it. So always look at this equation. Always think again, when we're talking about the sums of these and setting them equal to each other, don't be quick to plug in all the numbers. Always keep it in algebraic form, like the variables in there, because you can see if you don't plug in the numbers, they're equal to each other, right? The J and the G are the same because it's the same diameter and the same material. So because of that, we can cancel these out and then just set a very much neater looking equation, right? The TA times or is equal to 1.5 times the TB. So again, you probably could have done that math out by taking J times G and 400 millimeters, dividing that, but that will waste a lot of time during the exam. So if you keep it in algebraic form, you can cancel some of those values out. Okay, so now we have these two equations and we can solve them for each other, right? Just plug in this right here, and then boom, we can get TA. And then once we solve for TA, then we can solve for TB. And so we have our now two fixed moments, or sorry, fixed torques at the end of 180 Newton meters and 120 Newton meters. So this is good, but we're not done yet because remember, we're asked to find the maximum shear stress. And we do that using the equation shown right there. Luckily, J is the same and radius is the same because the diameters of the shaft before and after are the same. So we just need to find those values once. And we see that the max shear stresses are shown here, which are gnarly big numbers, right? So you make them a little bit smaller and prettier. And we say that it's going to be about 14.3 megapascals and 9.55 megapascals. So always look to simplify these, especially if the radius is the same on both sides and if it's the same material on both sides. If the radius is the same on both sides, and if the material is the same on both sides, and the shear modulus is the same on both sides, this equation gets a lot simpler because you can cancel these things out. Yeah.
I'm more just like, it's not really this question, like a simple question. In like real life, is twist deformation, does that cause elongation?
Well, no, maybe for some materials.
Poisson's ratio kind of thing.
Yeah, because the shear would cause like some dilation. So I'd imagine it would cause more of like, yeah. I mean, twisting would cause a shrinking in diameter, so it would cause a pull in some of them. I don't know. That goes into the material science side of things. If I find some information, I can let you know about it. Okay, so a little extra added torsion problem. So this was not in your homework, but I think it's a helpful one to kind of visualize the static side of it again. So I would recommend going through this one again, like just solving it on your own, just to make sure you follow the steps of it. Because this is a type of problem that looks, I use the word gnarly way too much, but like it looks crazy. And you really have to read the problem to solve it. But we are told that it has a rod of 1 inch, so it's constant throughout. And this rod has a self weight of 10 pounds per foot, right? So it's this little angled thing and it's fixed here at the end and free on the other side. We're asked to determine the maximum torsional stress in the rod, not the road, at the section located at A. So A is right here. And we want to see this is only due to the rod's self-weight. So for this, it is a solid material, has 1 inch diameter the entire way, and it has a weight of 10 pounds per foot. So what we'll first do is make a cut at A, and we're just going to draw the statics out that way, right? So we have this cut at A, and if we make a cut at A, we have this torsion, this torque at A, and this is applied across the centroid X of that center, right? Because this is what we need to find is this TA. What we need to find is T max, but remember this equation here, we need to first find the torque before we can find the stress. So what we are told is that it has a self weight of 10 pounds per foot, which means off of this here, we have essentially a distributed load. Any of this material outside of this axis X, the centroid of that point where the torque A is applied across, has this self weight, 10 pounds per foot. Now, technically there's a self weight here, right? But this self weight shown in red that I just drew, this is acting on the centroid of the distance that, or of this, the axis that we care about. So remember, a torque is a force times a distance, or a force offset of that distance of where that point is. So the self weight right there shown in red, this is acting at a distance 0. So there's no torque applied from this. Just like how we have, if we have a moment acting on the support reaction, or sorry, if we have a force acting on the support reaction, it doesn't create a moment at that support reaction. It's not until we move the force away that we see that twisting, that torquing. So all that said, the thing shown in red there, that 10 pounds per foot, that's what we care about. And then we would treat this and we'd want to find the resulting force from this. So the resultant force F across this whole length, and the center of this, or the center of that, is going to be 2 feet, right? Because this is 4 feet length in total. So the resultant force is 10 pounds per foot times 4 foot of material, which is 400 pounds. And that 400 pounds is acting 2 feet away from the centroid axis that we care about. So we'll do the summations of moments, or summation of torque across this X axis that I show there.
40 pounds?
Oh, it is 40. Yeah. 10 times 40. My bad. Put too many zeros there. I made this problem like 10 minutes before class, so there might be more errors. So keep awake. Okay, so and that is also a 40. It's the con of copy and paste. So yeah, 40 times 2. So the torque, again, this is because of this force being applied 2 feet. So that's where this 2 feet is coming from. So besides that, that's the only thing creating a torque, because there's no other external loads, and the self weight of the bar between A and the corner is acting on that centroid, right? So for this, we can find TA, 80 pounds. So at least I did the math right there, 2 times 40. And then what we need to find now is the shear stress. So I like this problem because the terminology is a little different. This is taken from your textbook. Also, this is something that you might see on different FEs, or, they switch it up every once in a while. Torsional stress in this case is shear stress. What you want to be looking for is, again, the term stress here, right? So we know it's a stress. That means it is the torque stress, or the shear stress caused by torque. So this is caused, another way thinking about this is stress caused by the torque, or T. So look for the one that has the T in the equation, right? So this, or also has to find the maximum torsional stress. So remember, I drew this earlier, but max torsional stress occurs on the outermost fibers. It has this gradient away from the center axis. And so this max is going to be distance C, which I'm just saying is the centroid, like the distance from the center of this shape up. So the polar moment of inertia in this is a solid shaft. This is pi divided by 2, r to the 4th. So that's what this r is, right? Because this diameter is 1/2 or 1 inch. I'm just going to keep it in algebraic form, again, keeping the pi in there. Don't factor the pi in there, so you just have a bunch of math errors. We're going to put that in the denominator. We have 80 pounds per foot, or pound per pound foot, times that c, or radius, 0.5 inch, which is the outer distance to the outermost fiber, divided by j. And what we see is that we'd have to put this 12 per 1 foot to cancel out the foot with the inches. And what we have is 4.89 KSI. Sorry, I should have highlighted here. So this would be the maximum shear stress developed in A. So conceptual question here. What if we asked, all right, what is the maximum shear stress applied at B? How would we solve it? Or what could we find for that? B is right here. It would be the same. There's no difference because there's cutting it between A and B. There's no change and there's no external loads applied differently in it. So if we were to draw the max shear stress, and this is across the axis X. So all we care about is what is coming out of that axis, distance away from the axis.
We could have done this whole thing if the TB is at BA as well.
Mm-hmm. Yeah. The only reason I asked this is because it said located at A. It's kind of chopped up there, but yeah. Okay, so I know this one wasn't on your homework, but I think going through it and especially understanding what torsional stress is and where the maxes are will be helpful. All right, let's go to one that should be more familiar. So drawing the shear and moment diagram for the beam shown below. And as I mentioned before, on the exam, I'm not going to ask you guys to draw the shear and moment diagram. On the FE, there's no drawing. Luckily, it's computer-based exam. You don't have to draw stuff. But what you may need to do is use shear moment diagrams or draw one on your own to solve for something. But I'm not going to ask you to submit it. So you don't need to bring a straight edge or a pencil or worry about scaling or anything that way. So in this fact, when I say draw the shear moment diagram, it's really just for practice and illustrative purposes. Knowing how to do it quickly will help. All right, so for this, the steps for this is, all right, we have external loads applied. We need to find the resultant loads at A and B. So the reaction forces, resultant load, support reactions, then we find shear, and then we find the moment. And remember, the moment is just the area of the shear curve. So first, the resultant force from the distributed load here, 150 pounds per foot, right? This is easy statics from here. This is applied across a 6-foot section of our beam. So really we're saying that this is about 900 pounds and it's acting in the center of this rectangular distribution. So 900 feet acting there in the center of it. So from the equilibrium or the reaction forces, we know there's a vertical force at A, there's a vertical force at B. So let's say counterclockwise CCW, counterclockwise, I just didn't want to draw the arrow. That's going to be our positive direction. And let's do it at point A. So, and we take our finger, we pretend we put a little pin here and we see what is it causing, or how is, when we push on each thing, how is it causing it to rotate? So we have a positive direction, 350 times 4. That's the one on the far left. Then moving on the right side of the support of A, we have this 900 pounds times 3 feet away. That's because, again, it's acting in the center. And this is causing it to rotate clockwise, which is negative. And then we have that we have the BY causing it to rotate counterclockwise. So that's why it's plus. And then we have the 200 pounds acting 10 feet away from point A. And we set these equal to 0 and we solve for B. So BY is going to be 550 pounds. Positive, meaning it's in that direction that the arrow is showing. We then do summation of forces of Y direction, a little bit simpler math to solve for AY, which is positive, again, showing that the way the arrow is showing is 900 pounds. So we have our support reactions. The next step now is going to be draw our shear diagram. And then once we've drawn our shear diagram, calculating the area under the curve or the function of our shear diagram, and knowing that that is the moments. And then we want to check and make sure that all the moments at the end of the beams are 0 because they are free on both sides and there's no external moment applied. That's just like the check, just to make sure you're drawing it correctly and doing the math correctly. So we're going to go through and draw the shear diagram now. So again, shifting it over, let's draw a shear diagram. Think always it's easiest going from left to right. So for the starting there at x equals 0, right off the bat, we're knocked down 350 pounds. And then between that external force and the support reaction, nothing changes. So it's nice and easy. And then right at point A, we get pushed up 900 pounds. So 350 or negative 350 plus 900 is 550. And then as we're going through this distributed load, as we move from left to right in this distributed load, we're getting knocked down 100 feet or 100 pounds per foot. So in total, we know it's going to be 900 feet down. But remember, the rectangular distributed loads produce triangular shear. So as we move along here, going left to right, we see a slope. It's just a function of it down to 350 below for negative shear. And then right at point B, we have 550 knocks us back up. And then nothing changes in between this. Sorry, this should be 550. It's plus 550 from the support reaction. I think that math is right. Yeah. And then nothing changes, and then 200 knocks us back down, and we're back at 0, right? So that's our shear diagram there. So remember, shear, if you don't want to think about it math-wise, shear is just equal to the derivative of the distributed load. So the way of saying that is WX, right? So the weight, or 100, it'd be negative 150 times X. So negative 150 times 6, which is the X, is 900. So that's like mathematical form, how you get that, and why you get it from a triangular distribution there. Yeah.
What's the point of the, where you have like the 4 feet? What is the point of the X there? Like, are you just for like?
This is just saying this is the starting point. Yeah, I was just saying this is where I'm starting here. So there's no real purpose of it. I think just going from left to right. Okay, so this is our shear diagram. Let's start calculating the areas underneath each one. So I highlighted this little first section here, right? This area of a rectangle, base times height. Remember, just keep it negative. So negative 350 times 4 feet. It's negative 14 pound-foot. This area is a triangle, but we don't know the intersection point. So we need to know this triangle and solve them so we can find the areas of these triangles. So what we're going to do is we know the total distance between these triangles is 6 feet, right? So we're going to say one of them is X and the other one is 6 minus X. So then using like triangles, we can solve for them knowing that these angles are the same angles here, right? So geometry, back in action here, like triangles. I did the math out for you. 550 over X is equal to 350 over 6 minus X. You foil, or not foil, gosh, when was the last time somebody's foiled something? That's crazy. First outside, inside last. Woo, throwback. So yeah, you do this math out, you cross multiply, then solve for X. And we say X is 3.7 feet. So now that we know this distance X, we can solve for the area of each one of these individual triangles. So the yellow triangle is a positive 1,008 pound-foot. And then the blue triangle is a negative 408 pound-foot. And we're back with this simple rectangle, this positive one, which is just 2,000, or yeah, it's going to be, get out of here, 800 pound-foot. So we're still on the shear, but we're calculating the areas because then these are used for our moment diagram. So we'll put these off to the side. Now let's calculate our moment diagram. We know we're starting at 0 on the left, and then we go straight down to negative 1,400 pound-foot because that is area 1. And since this is a rectangular area in our shear, that produces a linear or a straight line function or a triangular function for our first point. And again, the way thinking about this is imagine you're dividing this area up incrementally, each whatever inch or each millimeter, whatever we're subtracting an equal amount of area. So that's why we're getting this steady slope down. Now our moment's at negative 1,400 pound-foot. Area 2 is 1,008 pound-foot. So we're going to add that, and we should end at negative 392 pound-foot. Now, this shape, though, is important. And if we think about as we're adding these here, what is happening with the area as we are going from left to right in our triangle? The area is getting larger or smaller? Yeah, the area is getting smaller, which means we're adding less to our total moment. So that means the function is going to start really fast because we're adding a lot and then slow down because we're adding less at the end. So we have this concave or convex, gosh, I can never remember, convex like hill shape. And so this ends at negative 392. And then we have area 3. So we're going to subtract 408. And this is leaves us at negative 800. And in this way, we have negative area. As we incrementally move along, we're adding or subtracting more and more area. So we start off slow and then we ramp up and we have a steeper motion at the end than when we started. And so this gives us this downward concave shape. Convex, gosh, just ignore all of me trying to explain ramps. We have a hill, not a half pipe. So then now that we're at negative 800, our last area is positive 800, and it's this rectangular, which we know is going to produce triangular. So boom, we have this beautiful little moment diagram shown here. Now, this is what I asked you to solve, but like for this, where would the max be, right? Max right here would be this 1,400 pounds. This would be obviously our max produced here. And the location of that, again, you can always see the maximum or the minimum of the moments are where the shear is equal to 0, right? So you can even see in here, this is an inflection point because the shear is equal to 0. All right, any questions so far?
Yeah. When I did mine, I knew that shear was 0. I just did one continuous curve without having like inflection point in the middle. Even though it's there, I did the integral from 6, so like slope.
Okay. So as long as you could still find the point, the max in the center, but then yeah, if you set it up as a function and do an integral, then just know like if you want to find it at a certain point to plug in that x value in the integral to do it. But yeah, you can do it whatever way you'd like. You want to do the math way. Okay, shear moment. Number 4. This was on your homework 3. This one is important because we have an external moment applied of 35 kips, and we're asked to draw the shear and moment diagram for the beam shown. So again, just drawing it, same steps, but we have to note in this, we have an external moment applied of 35 kip foot. So when we're talking about resulting loads, we need to make sure to include this moment, and this will affect our support reactions. It won't affect our shear, but when we're doing our moment diagram, we have to include this 35 kip foot external moment too. So external, exterior moment, whatever you want to think there. So let's talk about the resultant force from the distributed rectangular load. You guys are pros by now because you all passed statics. 5 kip per foot times 5 feet. So the resulting point force is 25 kip. And this is acting in the center of it. And this is 5 feet or away there. Just out of curiosity, let's just say this was a triangular distributed load. Let's say for some reason I was super angry when making the exam. This is a triangular distributed load with a distance base. We know how to find the resultant point force, right? This would be
1/3 from 2/3 from.
yeah. So make sure you can recall that too. Hopefully you taught that in statics, right? This would be 2/3 of the base. Just move this here. 2, 3 times the base, or whatever that distance b is, or 1/3 going from left to right. So yeah, that's just making sure you guys are aware of that. All right. So for equilibrium forces, let's look at the support reactions. We just have A and B. Let's do the summation of moments at point B. So on the far right, you could do point A. I'm just going to do point B. And we're talking about the counterclockwise position is going to be positive. So we have a negative 35 kip right there in the center. And remember, there's no distance away from point B, because right now that 35 kip is that 35 kip foot from the moment, that's already in the units of moment. So if we multiplied that by a foot, it would be kip foot squared. It doesn't mean anything. So for external moments, we don't multiply it by a distance away from it. But what we do have to care about is the sign notation. So since I said counterclockwise is going to be positive, this is a negative kip foot as shown there. So the AY is acting 10 feet away, and we don't know that value of AY, but this is causing a negative direction because it's clockwise. And then the 25 kip resultant force is acting 12.5 feet away, and this is causing a counterclockwise rotation at B. So that is going to be a positive value. So we solve for AY of 27.8 kip, and then we do summation of forces in the Y direction to solve for BY. And the BY is negative, which just means the way I showed it with a positive arrow going up is really the other way around. So right here, you could do a couple things. You could either rotate the arrow and put it positive, or you just keep the arrow pointing up and do that value negative. But make sure you don't do both. I've seen those mistakes sometimes where it's like, oh, this is negative 2.8. So then you rotate the arrow downwards, but then still have it as a negative 2.8 when you're drawing your shear diagram. So make sure you do that correctly. So the next steps would be draw our shear diagram. And then just as we did before, knowing that the area under the curve of the shear diagram is our moment. And then we want to check that the moments at the end of the beams are zero, since there's no applied moments at the end and there's no fixed. But we can't forget about that external moment applied in the center. This will change our moment diagram as we are going between A and B. So let's start with our shear. Going from left to right, so starting at the very end and remembering everything is in the units of kip here. So we start at 0, and then we have that minus 25 from our distributed load, that's triangular. And then at point A, we get bumped up 27.8 kip. So now we're at 2.8 positive. Then nothing changes across that entire way because the moment does not have a shear force applied in it. So the external moment is just an external moment. There's no shear in there. So that stays the same. And then we have that negative 2.8 kip or 2.8 kip downwards that kicks us back at 0. So you'll see right here, I just switched the arrow downward and said it's a positive 2.8 kip. So it ends back at 0. So let's calculate our areas. This triangle, 1/2 base times height, that's where the 0.5 is coming from. And the reason it's negative is it's because it's below the value. So Vx it's a negative value. So 25 kip times 5. So that area is going to be negative 62.5. The rest of it is going to be positive, which is going to be 2.8 kip times 10 foot or 28 kip foot. So we have those two. Let's put those off to the side. Keep in mind too, it looks like this over it. So remember, when we're drawing our moments, this first part is a negative decreasing area. As we are dividing this up, we're getting more and more negative area. So the slope is increasing. So we have this like kind of increasing slope here. And then as we get to this positive area, we can't forget that we have this external moment of 35 kip applied. So before the external moment, this area 2.5, we have half of that area 2. So 27.8, this is half, right? Half of that, because we're only talking about this area before we get to this point. So this is going to be 13.9 kip or 14. And right, since it's rectangular, it's going to look like this slope. And then right when we have this 35 kip foot, we have a positive moment. Now, I didn't mention this in class because we haven't come to an example problem like this, but in statics, remember when we have external moments, we have to follow the conventional sign notation, plus minus sign notation. So what is important, or the thing to remember, is that half pipes, right? Like any skaters or something, half pipes are fun. Half pipes are positive. So if it produces a half pipe shape, meaning the bottom is in tension and the top is in compression, as shown there, then that is a positive bending moment. So right here, since we have a clockwise moment, this is producing, like this here, this external load, this is producing a positive moment. So this is going to make it go up 35 kip foot. So this is important. At the very beginning, when we did our statics and we were saying, oh, counterclockwise is negative or something, like that's just for my own personal math. When we're talking about external moments compared to like a moment diagram, then we have to follow the rules of what a positive value is. So regardless of what I said before, it's the same thing how when we were saying like when you make an internal cut, right? You have to say this is a positive shear and this is a positive moment. It's essentially the same thing for external moments too. So you can see right there, depending on what side you cut it on. Sorry. Okay, so we have that positive moment. Of 35. So now we're at negative 16.6, and then we move up here, and this gives us back at 0, which makes sense. So now this is our moment diagram here for it. So remember how this 35 half pipes are positive. Roll-ins are fun, but half pipes are more fun. So think about it this way too. Like the deformed shape of this would look like this, right? So if there is like what this means from this moment diagram is that we have it's negative the entire length, right? See how this is all negative. There's never a positive moment. And what I want you to think of, instead of like thinking, oh, there's just a negative number, what does this physically represent? A negative moment means that the top of it is going to be in tension the entire way, and the bottom is going to be in compression the entire way. That's what a negative moment essentially represents. So like, again, problems on the FE, which by now you should know this is hint for problems on our exam. Like you could be have a moment diagram like this and be like, in what section do we see the bottom? In what sections are is the top in compression and the bottom in tension? You know, like that would be where there's a positive moment. instead of a negative moment. So reading the moment diagram and understanding the physical meaning behind them is important, just as equally as important of just drawing them and getting the numbers right. Okay, fun. Let's look at another fun one with more external moments here. This is that crazy box one. All we have is external loads or external moments applied. So we have a clockwise 15, counterclockwise 10, and a clockwise 15, and then we're given the cross section there too that I'll summarize and make it look prettier. So for the same steps as we've done before, let's do the equilibrium so we can find the support reactions at AY and BY. So we only have external moments. Remember, these external moments are not multiplied by distance. I always see that on this exam. So do not multiply external moments by distance in statics. Sorry, that says do not multiply by distance. All right, so we have 15, negative 10, plus 15, and then that BY, because I said positive direction is clockwise, just meaning this direction if you don't know how analog clocks work. You guys probably, yeah, never mind. Nobody uses analog clocks anymore. So,
I do.
okay. What? I don't even have one in my house. I want to teach my kids how to use it because I'm like, I just look at this, but I don't actually look at that. I just look at the number on the bottom. Anyways, all right. So BY, if we do this math out, 2 kip. So summation of forces in Y direction, super easy, right? Because there's no external forces in the Y direction. So AY must equal BY in the opposite direction. So there we go. We got 2 and negative 2. So next steps would be draw the shear diagram, area under the moment, all that stuff. Question for this is, yes, you could go through the whole process of drawing the shear diagram, but think about simplifying this here. All we have are external support reactions. We don't have external forces aside from the moments applied. So for drawing the shear diagram, really, it should be pretty simple. It's just down 2, over, and then up 2, right? So always think about ways to simplify this. Yes, you could go and draw the entire thing, but knowing that the shear is only from the support reactions will help you simplify this and calculate the area here a little bit better. Again, just showing that the shear right here is negative 2. So if we say the moment is the integral of shear, doing it Sammy's way with an equation in math, then the moment is going to be negative 2x. So for this, keeping in mind that we have this whole half pipe positive direction, so this is going to cause that direction, right? So we see this is a half pipe that it wants to do. This is going to be causing that type of rotation, which is a negative. And then this one is going to be causing it to go that direction, which is positive. So we have to make sure we keep those over external moments the same direction. I say half pipe positive. If you want to just always remember clockwise is positive, you can also do that for external. But I think it's helpful to know the meaning behind that. So keep in mind the reason why I have these little steps, right? The negative 2x. That's because I said here, essentially it's just the area under this. We know it's 2x. You could do the math and cut it in half and say 2 times 5 feet is 10 feet. And that's basically what we're saying there. And then 10 kip foot knocks it down to negative 5 and vice versa here. So what this is saying is we have, what is our max moment from this? Yeah, it's going to be 15 plus or minus, right? Because what we care about moment, we don't care about plus, or we don't care about the direction per se. What we care about is the magnitude. So in this case, luckily it's symmetrical. So it's going to be 15 hip foot plus or minus, but you'll see in the next problem why that might be a different story. But let's continue on this one. So for the moment of inertia, since we're asked to find the moment of inertia, point B here, for the cross-sectional area. So it's a rectangular shape is 1/12 base times height cubed, and this equation is given to you, right? But this is assuming a solid rectangle like this. but you see we have a little hollow section. So they cut this section out. And so the way we solve for the moment of inertia is we take the larger section and then we subtract out the smaller section, this empty air void area. And that empty air void, it's a little hard to read it here, but it's 8 by 6 inches, right? So the walls of the panels, thicknesses is 1 inch. So it's a little bit of ugly math, but hopefully you can see where the base and the height is for each one, right? This is the base, that's the height, and then we subtract out the base and the height on the other side too. And if we plug this into our calculator correctly, we get a moment of inertia for our entire cross section of 410.7 inches to the fourth. Did I do that wrong?
No.
So keep in mind what I'm saying here. This is in the X direction across the centroid. That's what that little C is saying. It's bending across the centroid. Okay, so the max bending stress. Our stress due to bending, or axial stress due to bending, is this equation. Remember, if we zoom in, what this actually looks like is our centroid is right here. And what this is a axis coming out of the cross section. So I draw it just because I can't draw it in 3D, but this is a cross section. Like imagine this is like the place here. This axis is coming out of the centroid and the stress is applying normal to this force. So this is called our neutral axis. This is out of the cross section of the at the centroid. The moment is being applied across that axis, and it produces an axial stress, or a stress that is normal or perpendicular to that cross section. Based off of the bending shown here, it's going to be in compression at the top and then tension in the bottom. And so the max stress always occurs on the outside fibers or the outside edges, right? So this distance away is going to be C, our centroid. So for the equation there, that's where that C comes from. So remember, this is the outside, so that's 10 divided by 2, which is 5 inches. And then the moment that we found from before is 15 kips. And then our moment of inertia is 410. Now, if you look at this, we have feet and we have inches, so we need to make sure to convert everything to get into inches so we can get our value of KSI. And the reason I say plus or minus 2.19 KSI is because remember, that is this stress right here, and then there's this stress down here, sorry, that is equal. Now, when would this not be equal? This would not be equal if our centroid was shifted at all. If that distance to the outermost fibers on the top, C, was different than the outermost fibers on the bottom. And that only occurs if our centroid is not in the center of our shape.
Would that be like with like the T-bone?
Yeah, yep. And so the only time you have a centroid not in the center of our shape is if it's not symmetrical on top and bottom. So you have it separated. I just said the word set like 12 times in there, but centroid, central, symmetrical, I'll do, but one of the S's is an S and the other is a C. For anyone who learns English as their second language, I'm very impressed with you because it is not, there's no rules. It's the worst. I'll bring stickers for everybody that was. Centroid, central. So yeah, whatever. Okay. All right, speaking of which, let's do it a problem like that. So this is another one of those extra ones where we have a non-symmetrical problem. All right, so we have a T shape. It's the cross-sectional dimensions are there. I know it looks a little crazy with that moment max, but I'll show what that means here in a second. We're told that it's exposed to a max bending moment of positive 10,000 kip inch. So we're asked to also use a factor of safety of 2 and determine the maximum allowable tensile stress of the material. So a little flashback to extra credit on last exam, but factor of safety does not go away as a civil engineer or as any engineering. So we have our axial stress shown here in this equation, first page. And we also have factor of safety of 2, which is very important. We have to remember that the allowable stress is always less than the applied stress. So we divide it by the factor of safety. There was a lot of like issues on exam one. Oh, just remember, if it's safer, it has to be less. So if you're applying a factor of safety, the ending stress needs to be less than what you calculate. Okay, so first we need to find the neutral axis and geometric properties, because unfortunately, it's not clear where the centroid is for this, right? We have this T shape. The centroid, we're just going to say, is somewhere here, but we don't know that distance. So in order to find this distance, we have to first set a reference axis, and we're saying this bottom purple is that reference axis here. And to find the overall centroid, y bar, we have to use this equation. And there's a lot of numbers in here, so go back and make sure you know how to calculate this. All this is saying is we divide it into individual rectangles on the numerator. So that's that sigma, that summation. Each one of those individual rectangles, we know where the overall, or where we know where each one of those individual rectangles, we know where the moment, or sorry, not, we know where the centroid is. I'm about to draw on this anyways, but we know where the centroid is with respect to that reference axis. So we take each individual centroid and then we multiply it by the individual area. And then we divide it by the total area. So hopefully it's clear when you see the math how I'm getting those numbers. This 13, this is because this centroid here is 13 inches from our reference axis. So it's always just relative to the reference axis that we set. I know I drew a bunch on that, so I don't want to draw more on it. All right, so finding the centroid from the bottom is 9.5 inches. So now we're going to say this is 9.5 inches. Now the trickier part is finding the moment of inertia of this shape. So what we need to do is use the parallel axis theorem. There's a bunch of Greek stuff in there, but remember, all we're doing is dividing this T shape into two rectangles. So the two rectangles have their own centroids here. And this y subscript I, in my previous notes, I said y inye, right? The little sig like thing right there. I don't know if I'm pronouncing that right? Y inye, little tilde thing on the top. All that is the distance from each individual centroid to the overall centroid. And remember, we have to square this. Don't forget to square that value because I see that error a lot. So we can find the area of each individual one. We can find the moment of inertia of each individual one. And all the parallel axis theorem is the sum of all of these points individually. So I'm going to go through that math here. I didn't put units in there because I didn't want to scare you, but everything is in inches. And remember, don't forget this squared here at the end to find the y inye. So I suggest going through this and making sure you understand how to get this 844 inches to the fourth using the parallel axis theorem. Remember, all this is two rectangles. This whole thing at the top, or sorry, yeah, this is the top rectangle. No, this is the bottom rectangle. And then this is the top rectangle of our T. Because it's 1/2 or base times height to the fourth. So this is, yeah, all over it. Okay, so we're asked to find the tensile stress of the material. Remember, a positive moment, as shown here, this produces a half pipe. So this means it looks like this, which means we have compression on the top and tension on the bottom, right? So if we care about the maximum allowable tensile stress, would we care about the top or the bottom? The bottom, because I said so on the slide. So remember, this is the moment that's applied to it. The bottom's in tension, the top is in compression. So the way we draw our axial stress for the bottom, which is all we really care about, is this section here, which would be negative 112.6 KSI. And the only reason it's negative is just because it's in tension. So if we did care about the top, we could calculate that. We have the same max moment of 10,000 kip inch, but now we, instead of the Y of 9.5, we do this distance here, which is 14 minus 9.5. And this would produce 53.6 KSI, which follows and continues this way. So you can see in this case, since it's not symmetrical, our top axial stress is not equal to the bottom axial stress. So if this was symmetrical, and if our neutral axis was in the centroid or at the center of it, then we would have it equal to each other.
Would you expect us to
Draw the like this? No, you don't need to draw it, but like just know that this value is that value. This value is this value. And obviously, you know, here is 0. So, I mean, you can draw it pretty easily. It's just 2 points on a line, but. Okay, so remember though, we're not done because we have to find the factor of safety, the allowable. So this is the top. We need to divide this by 2 to get the allowable tensile stress of 56.3 KSI. So don't forget if you have a problem with factor of safety in there. Okay, I'm gonna go through this one really quick. I understand we have 1 minute left, but this solution's also posted, so you can view it there too. This was on your homework. For the steps for this, we're going to visualize this canoe as a simply supported beam. We find the reaction, we find the shear, we find the max moment, and then we determine the radius of curvature to solve for the vertical deformation. Here in this case, I'm just saying that vertical deformation is this delta value. There's not an equation associated with this. You just need to think of it from a geometry standpoint. So we're going to visualize it like this. We have this point load of 275, and then just knowing that since it's in the center, each reaction force is going to be half of that, which is 137.5. So if we're drawing our shear, straightforward, over, down, over, up, we can find our moment at the center is going to be the maximum, and it's going to be a value of 1375 pound-foot. That's going to be our max moment. So we don't even need to find or draw our moment diagram if we know that this is going to be the max. So determine the radius of curvature. The equation I gave you is this. Remember, this is 1 over the radius of curvature is equal to the moment over EI. Now, what does this radius of curvature physically mean? We can solve it numerically, but what this radius of curvature means is the arc radius that is produced by the deformed shape. So one of the assumptions is that a deformed shape, shown here, is going to follow an arc. And we know that an arc is just a section of a larger circle that's not fully drawn, right? So that radius of curvature, rho, that Greek letter rho, is the radius of this arc, this large arc here. So if we talk about the radius, we know the points at the end, but this also means that the point in the center is the radius, because that's how a radius works, right? It's the distance from the center along all the points of the circle. And so what we need to find is this max vertical deformation in the center of it. So let's look only at that area here. And we have to go back to geometry. We know that the radius of curvature, we know that value. We know this X value, but what we need to do is find this Y value. And what we know too is that this is a beautiful right triangle, and we have a buddy named Pythagoras who solved this thing a long time ago for us. So if we look at half of it, it looks like this. The radius of curvature is here, that Y is here, and then the 10 feet, which is half of our canoe, is here. So to find this delta, or this deformation, the sag, this is the radius of curvature minus Y. Because remember, this whole thing is radius of curvature like that. And I know I didn't draw it very well, but that's, that's how an arc works. It's just over accentuated. So the radius of curvature is 48 or 418.89. A squared plus B squared equals C squared. In this case, our C squared is going to be the rho squared, which is radius of curvature. So we need to make sure we set the equation up correctly to solve for y. Our y is going to be 4180.1 inch. Also note, I switched 10 feet to equal 120 inches because our radius of curvature is in inches and everything in this needs to be same units. So fun geometry, we're in a 3000 level engineering class and we're just using Pythagorean theorem, right? But this is how we can solve for the deformation in the center by subtracting the radius of curvature from that y. And it should make physical sense, right? We have these big radius of curvatures, but the resulting deformation is very small of 1.72 inches. And that's our answer. So I went through this one really quick. Please go through that. Remember, for exam 2, recall stress and strain graphs. I'm not saying it's going to be on there, but some of the concepts from stress and strain are still going to carry through. Know how to efficiently create shear and moment diagrams. And then also, even more so, know how to read shear and moment diagrams. Practice calculating the neutral axis, where the centroid is. And then also know how to efficiently calculate the moment of inertia. Practice doing that parallel axis theorem. I will see you guys on Thursday.